Okay, so I'm going to quickly finish up the notes today. We're going to talk about the mass spectrometer. What you can see down here is this is the kind of the internals of the mass spectrometer, because these are machines. These are very expensive machines that you can have like in a university setting, or you can have in a like an actual work setting, like if this was what you were doing for a job, was figuring out samples. This would be in that type of a setting. These are too expensive for a high school setting. If you go to Google and you do a quick search for mass spectrometer or mass spectrometer machine, which I did here, you'll see that you just get pictures of machines. So this type of thing would sit on a table. You can kind of see the size here. This is a good video, this Princeton chemistry video about mass spectrometry. I'm actually going to show this in class, so you can look that up. It's on their website. It's actually trying to entice you to take chemistry from Princeton because they have such a great lab setup. And so you can see all of these devices and see the sizes of them. They're not small and they are not inexpensive. So if you look here, you can see the idea of the screen attached, which is giving the readout. And you kind of see the readout on that one. So anyway, that just kind of gives you a general idea of what the heck these things are. IB doesn't really want you to be able to use these, because obviously you're not going to have access. They just want you to kind of understand a little bit about it and then be able to do some simple math. So let's take a look at it. So we've got our sample and we put it in to our machine. So the first thing it does is it's going to turn our sample into a vapor or a gas. It's then going to add a bit of a charge, so we have an ion. Then it's going to push the particles of our sample past a magnet. So if you have particles and they are heavy, they're not going to deflect as well because they're just heavier. They resist the magnetic force. So your heavier particles are going to be deflected less. And so we could say maybe the heavy particles are over here, and so we go through and they don't deflect as much, and so here's our heavier particles, and so they're going to maybe be hitting in that area of the plate. So as they hit, you would have the little detections show up there. Now let's say you had a lighter particle. Well, the lighter particle would go through, but then when it gets here, it would be deflected a lot more, because the lighter particle is just going to be easier to move, and so it says right here it deflects the lightest ions the most, and then they would be hitting down here and the machine would be getting detections there. It basically tabulates all this data and spits out what's called a mass spectrum. Now, a mass spectrum is what you're going to be looking at in class, and it's going to be provided, and you just have to be able to do a quick bit of math. So let's kind of track down here and look at that. Okay, so you have two types of mass spectrum. You can have one like this where they have the percentages, and then they even gave us the percentages of each of the isotopes. Or down here, same thing, except they didn't give us the percentages. We'd have to kind of come up with them. And then you have two components. You have the percent abundance, and then over here on the x-axis, we're going to have our mass. So it's mass versus percent. So basically, the more the particle hits the detector, the more the percentage is, and then it spits out that data. So this is a very simple one. This is an element. And so it's going to have two components, and we're just going to basically take percent times mass plus percent times mass, do all that, add it up, and you're going to get an average. So they said 77%, so that's kind of like where this line's coming over, and then they're saying that one's 23. So that's where we're going to get our data. So we'll do the 77 first. So the 77 weighed 85. So I'm going to go 85, and I'm going to multiply that by, in my calculator, 77% would be 0.77. And then I'm going to add that to my 87, and it's going to be multiplied by 0.23, which is 23%. And then we're going to go ahead and run that through our calculator. And that's going to literally be the answer. So 85 times 0.77 plus, make sure you use parentheses, so 85 times 0.77 plus, in parentheses, 87 times 0.23. And I got an answer of 85.46. So let's see if this answer has any chance of being correct. So the way you do that, you look at your data. 77, 23, it's got to be between 85 and 87. So my answer as an average has to be between these two numbers. 85.46 is, okay, that's good. Now let's look at the peaks. Well, I know that it's an average. So what I know is that it's got to be between 85 and 87, but the 87 is bigger than the 85, so it should be pulling the average away from the 85, but it should be closer to the 85 because 77% is 85 in terms of the mass. So the 23% is going to pull it forward a bit, but not going to pull it forward that much. And so you can kind of think, well, I'm probably in this area down here. Well, yep, there we go, 85.46. It's a little bit beyond 85, but it's still pretty close to 85. So what I tell students, answer should be pretty close to your highest peak, which was 85. But then you have to look at these and determine, are the averages pulling it forward or pulling it back? Now, let's say you didn't have any numbers, just had a couple of lines. You could come up with the same thing. So we can erase all this, and we could just do it with inspection, and then we can see how close we get. So let's do that real quick. Let's just do this with inspection. Okay, so in my mind, I'm thinking, okay, I don't have any of this labeled as percents. I just have lines, and I'm not going to have this, and I'm not going to have this. So if I don't have any of that, I just got a couple of lines. Okay, I know my answer has to be pretty close to 85 because it has the biggest line. But I also know that it's going to be a bit more than 85 because there's also a line at 87. So I would say it has to be 85 plus, but not that much past 85. And so basically, you know, I would probably guess 85.5. All right, so let's try that down here with this example 4. So what I would do is pause the video, take a look at number 5 and see what you think the answer is, and then go ahead and do the math and kind of verify. So that's what I'm going to do. So pause the video for a minute and see what you get. Okay, hopefully you looked at it, and now we're going to do it. So we're going to pretend like none of this exists right now, and all we have is these two lines. So 69 is bigger than 71. But they're pretty close, right? The lines are pretty close. I know my answer is going to be pretty close to 69, but I know it's going to be bigger than 69. And so, but this isn't, it's not like the lines aren't the same height. So it's going to be not exactly in the middle of the two. So it's not going to exactly be 70, but it's going to be pretty close. So I'm going to guess on this one that I'm probably going to be like 69.8, something like that. Like pretty close to 70, but a little bit behind it. All right, so let's verify. Let's do the math. And let's kind of see if we were right. We put down a number. Let's see what it is. So first of all, we got to like look at these percents and kind of come up with an idea. So when you're looking at this, you kind of take this across. It looks like about 60 and it looks like about 40. So we'll just kind of go with those numbers, 60 and 40. So I'm going to take the mass at 69. So I'm going to take 69 and I'm going to multiply that by 0. And then I'm going to go ahead and add that to 71. And I'm going to multiply that by 0.40. And then we're going to hope for the best. So here we go. We're going to have 69 times 0.6, enter. We're going to add that to 71 times 0.4. And we're going to see what we get. I got 69.8. I did not actually look at the key, and I did not, give you the perfect guessing answer by looking at the key. I actually did it, and I just got lucky, and it came out with the answer. But if you didn't have this data, like if you put down 69.7 or 69.9 or maybe even 69.6, those all would probably be right. So anyway, that's kind of how you do this with and without the labeled axes. So let's go down to the last one here before we end this session, example 6. And example 6 is interesting because it has a whole bunch of different peaks. And so when you have a problem like this, the first thing you want to look at is the chemical. And so they said Br, but what they said specifically was Br2. And that is interesting because it is diatomic. So if we look at the data they gave us, it's a little squirrely. We've got data down here at 79 and 81, and then we also got a 160, a 158, and a 162. Well, what's going on here is that it says, what do the 5 values represent? Well, they represent bromine in all of its different combinations. So you have bromine. Let's erase that and do it the correct way. You would have a bromine 79. You would have a bromine 81, and those would be those are atoms. They're not diatomic. But then the combinations you can create with the diatomics, there'd be 3 combinations. So there would be a 79 plus a 79. That's if you got two of the 79s to create a diatomic. So that's option 1. You could do an 80 and a 79, or you could do an 80 and an 80. Well, a diatomic with 80 and 80 would be, sorry, not 80 and 80, my mistake, 81 and 81. Sorry about that, 81 and 81. I put down 80 instead of 81. So let's fix that. Okay, try that again. So 79 and 79 is going to give you the 158, 81 and 79, 160, but if they're both big, it's 162. So you have the diatomic bromines, 3 of them, 1, 2, and 3, and then you have the 2 monatomic or non-diatomic bromines. And that's what all the values are. So what is the relative atomic mass? Well, you could just take the 79 and the 81, and you could look at the peaks they gave us, and we could come up with an answer. So let's go ahead and clean this up, give ourselves a little space. Overall answer is going to be a little tricky because the data is not particularly easy to look at, but if we look here, I mean, those are pretty much the same exact height in line. So so an individual bromine has to be between 79 and 81, and it looks to me like it splits it right down the middle. So we're going to say it's probably about 80. Well, if you look up if you look up bromine on your periodic table, you can just verify that. So if you look at the periodic table I gave you, go ahead and look at your bromine. It's going to be 79.9. So on my periodic table, from the periodic table, it says 79.9. So about 80 is right. So anyway, that's kind of how you do these. Before we end the video here, just again, they're going to have you read mass spectrums, and I guess the thing I would take away the most is your answer should be as close as possible to the highest peak, and you're not going to have to do multiple chemicals, just a single element. And so a lot of times they just want you to identify what the element is. And so in example 4, we kind of forgot to identify the element, so we should probably go back and do that real quick on these last 2 before we run out of time. You just look these up on the periodic table, so that's all you do. So you're going to end up with gallium here, and then on the mass spectrum of the other one, you're going to end up with rubidium. And you can look those up, and you'll verify that. So, all right, we're going to run out of time on this one. So this will be the end of this session, so you can work on that at home.